Now we will learn the next result is known as a Bayes theorem. To learn this Bayes theorem, first of all, you should know what is the definition of nowhere dense set. That means a set which is nowhere dense. You can add lots of points into it, then it will not be a dense in. You know what is a dense set? Dense set is A closure is equal to X. Like a forest, a dense. When you can say this is a dense forest, whenever you see, you will found a tree. So every point of that forest will not have a tree, but whenever you look at it, the forest, you will find a tree. So that is kind of things is there in the dense set. Here the set is nowhere dense. That means when you will see, you will have lots of, you can collect all the points, you can collect all the tree in that, then you cannot cover the space of the forest. So that's a nowhere dense forest, I can say in general language. So what is the definition of the nowhere dense set? A subset A of a metric space X, it's called nowhere dense if its closure has empty interior. That means interior of closure of A is pi. So in that case, we can say that a set is nowhere dense set. For example, if I consider A is equal to Z, set of all integer, and your X I'm taking as a real line with usual metric. Then what is this A closure? That is A union its limit point. What are the limit points of Z?
5.
5. And what is A? Is Z. So what is A closure? Is the Z. What is the interior of A closure? That means this Z. We know that it is 5. Okay, because you know that if you draw a neighborhood of 0 and it will not contain by the Z, you can found such neighborhood. Okay, so that's why this 0 is not an interior point. So the interior of Z is 5. So the Z, I can say it is a nowhere dense in R. So Z is nowhere dense in R. In similar manner, I can prove that N is nowhere dense in R. And so on. There are other. Also, very interesting result is there. Those who are doing they are making a presentation on that. The Cantor set is nowhere dense in closed interval 0, 1. If you define a Cantor set on closed interval 0, 1, then the Cantor set is also nowhere dense set. That you can try to prove by yourself. Now let me state what is this Bayes theorem is. It says that if an, a sequence of an of nowhere dense set in a complete metric space X, then there exists a point in X which is not any of the an. So I'm taking the sequence an is a sequence of nowhere dense set, and which is a subset of this complete metric space. Then there exists a point in X which are not in any of this an. For example, I can define this singleton set 1, then 1, 2, then or 1 minus 1. Let's say define this 1 minus 1, then 1, 2, minus 1, minus 2. If I define another sequence, then 1, 2, 3, minus 1, minus 2, minus 3, and so on. This is A1, A2, A3, up to so on. So this A1, A2 up to AN in general, they are nowhere dense in R as a subset of R. Then this theorem says that then you will find some points in R which are not in any of this set. The condition is this ANs has to be nowhere dense. So you can construct a set which is nowhere dense, and your space, the original space, has to be complete metric space. Then you will have such thing. Now, proof of this is is constructive. That means we have to construct a sequence of this sets, and we have to prove this statement. So for that, given that X is open, we already have X is open because it is a space and the space is complete, and A1 is nowhere dense. Then what we can say, so this is the situation, this is your X, and there is a one subset of this which is A1, which is nowhere dense. That means interior of closure of this set is phi. Then you are able to find out some neighborhood which is outside this A1, and I'm calling for this one is S1. So just simply, generally we are denoting the neighborhood as SR of X, but for time being I'm just denoting this as S1. So therefore what we can say is there exists an open sphere S1 of radius less than 1, such that S1 intersection with A1 is 5. So there is no intersection between these two. We can construct such thing. Now consider this F1 be the closed set, closed sphere whose radius is 1 by 2. Okay, so what I'm taking, there is a inside this S1, there is F1. So inside this S1, I'm considering this F1 set, which is a closed set because it is a closed sphere. We have already proved that it is a closed set whose radius is 1 by 2. So F1 is a closed sphere whose radius is 1 by 2 with same center as S1. Whatever the center of S1, inside that we are considering one closed sphere. Then consider the interior of F1. That means interior of whatever the set F1 is there. Okay. Now, what we can say in the next, since A2 is a nowhere dense, so there is another set A2 which contains an open sphere. So interior of this F1 contains an open sphere. Let's say that open sphere is S2 of radius less than 1 by 2 such that S2 intersection with A2 is empty. So there is one set A2 here. I don't know whether it is intersecting A1 or not, but it has to be separated from this, and inside this F1 we will have another radius, another open sphere whose radius is less than 1 by 2. Now in the same way as we have considered the set F1 which is inside this S1, we'll consider one set F2 which is inside this S2 whose radius is less than 1 by 4. So let F2 be the closed set, closed sphere whose radius is 1 by 2 with same center as S2, and consider the interior of F2. That means this. I will define another set F3. So we consider now inside that S1 there is a set. So we'll have F1 which is inside that, we'll have S2. Inside that we have another open sphere. So as since A3 is nowhere dense. And interior of A2 contains an open sphere with radius less than 1 by 4. Open sphere, let's say it is S3, such that S3 intersection with A3 will be phi. And in the similar manner, we will have F2, F3 will have F2 is a closed sphere. In that same manner, we have F3 is a closed sphere whose radius is 1 by 4. Then, with the same center as S3, and consider interior of F3. That means this. And so on. You proceed in the same manner. What we are constructing the sequence of closed spheres F1, F2, F3. And all these spheres is actually a sequence of decreasing sequences, because we have considered this S1, inside there is F1, inside there is F2, inside there is F3. The radius will be the getting smaller and smaller. So we can say, continuing in this way, we get decreasing sequence of Fn of non-empty subsets of complete metric space X. Then by end such that the diameter of this Fn, as we have seen that the diameter is here for F2 it is 1 by 2, for F3 it is 1 by 4, and if you go on, the diameter will be 1 upon 2 raised to n, which will tends to 0 as n tends to infinity. So we apply now Cantor intersection. This will satisfy all the conditions of Cantor intersection theorem, that each Fn is closed. Each Fn's are closed set because it is a closed spheres. Your X is a complete and the diameter is tending to 0. So by applying Cantor intersection theorem, there exists a point X in X such that X is belongs to Fn, or I can say it is an intersection. It is an intersection of all these Fn's. So this will imply X is belongs to each Fn for every n. But what is Fn? Fn is actually a subset of Sn. But the intersection between Sn and An is non-empty. That we have considered for each case. S3 intersection, A3 is non-empty, and so on. So we have constructed a sequence in such a way that, and this is true for every n. So what does it mean? X is in Sn, but it should not be. So this will imply X, it is not in An for any n. So we have proved that the point which is not in the point X which is in X, but not in any of this AM. So which completes the proof of this base here. Okay, so that is the proof. If you have any doubt, you can ask.